Hello, and for our last video in this series, we're going to talk about the root test for absolute convergence. So again, suppose we have any series. If we take the nth root of some absolute value of the nth term, and we look at that limit to infinity, just like we did with our ratio test for absolute convergence, that's going to be equal to some rho value. All right, if rho is less than 1, we can say converges absolutely. If rho is greater than 1, it diverges. And if rho is equal to 1, it's inconclusive. So instead of doing a ratio of terms, we're going to be looking at the nth root of a term and then applying that limit to positive infinity. And so, again, we have all of these tests. How do I know when to use what test? It's hard to know exactly which test to use without a lot of practice. But if we have nth powers, so some number raised to an nth power, the root test is a good one to try. All right, so we're going to apply the root test to investigate the convergence of this series from 1 to infinity of 2 to the nth power divided by n cubed. And so as I just said, and you see in this example, we have 2 to an nth power. So this is a situation where you might try using the root test. And what the root test says is we want to look at the limit as n approaches infinity of the nth root of the absolute value of a sub n. And that's going to be equal to some rho. Okay? Now, rho is either going to be greater than 1, less than 1, or equal to 1. And that lets us know if the series will be divergent, convergent, or inconclusive, respectively. So my nth term, if I plugged in n, my nth term is 2 to the n over n cubed. And my n values are positive. This is always going to be positive. We can leave our absolute value bars out in this situation because a sub n is always greater than 0. It's always positive. So let's look at the limit of the nth root. So the limit as n goes to infinity of the nth root of 2 to the n divided by n cubed. And we want to simplify and see what this is equal to. Well, I can apply that square root to both the numerator and the denominator, and the nth root of 2 to the n, those are inverse operations. So we just get 2 in the numerator. Okay, so I've got a 2 up here. And then I have the nth root of n cubed. And for the sake of making this look a little easier, I can say, well, that's the same thing as saying the nth root of n cubed. All right? That power multiplication is commutative. All right, so let's think about how we are going to deal with this, right? Because we are now dealing with the limit as n goes to infinity of 2 over the nth root of n cubed. So how does the nth root of n behave as we approach infinity? So I'm going to pull like a little problem out of here. We're just going to think about just this. And so I'll say, the limit as maybe x approaches infinity of the x root of x. And that could be the same as writing the limit as x approaches infinity of x to the 1 over x. So in this situation, we are looking at a 0 in that exponent. This is kind of the same as infinity to the 0th power. And we get the 0th power because 1 over infinity is equal to 0. So this is what we call an indeterminate power. And when we want to find limits of things that are an indeterminate power, we use a method in L'Hopital's rule, because we use L'Hopital's rule for indeterminate forms. Some people call it the limit chain rule, but essentially we're going to use natural log of the function. And I have a video about indeterminate powers and using L'Hopital's rule. So I'm going to write out how we get that this limit of just this little piece in our original limit that we're trying to figure out becomes 1. So what we'll do is we'll take the natural log of x to the 1 over x. And by the power rule, that is 1 over x, natural log of x. And so if we look at the limit of this, the natural log of our function, right? We're dealing with the limit as x goes to infinity of now the natural log of that function. That is going to be equal to the limit as x goes to infinity of 1 over x, ln x. So 1 over x, plugging infinity in there, we're going to get 1 over infinity times the natural log of infinity, which gives us 0 times infinity, and anything times 0 is 0. So in order to calculate this, our rule says that what we're going to do, since I used a natural log, I'm just going to calculate e to that limit, and e to the 0 equals 1. So the limit as x goes to infinity of the xth root of x equals 1. And I encourage you to go back, look in your book at L'Hopital's rule, indeterminate powers, and I also have a video about L'Hopital's rule and indeterminate powers, but we did that in Calc 1. So this expression, which let's go back up here, this expression in the denominator, as n becomes infinitely large, if I looked at plugging infinity in there, what I get is 2 over, we just said that value is equal to 1 cubed. So this is equal to 2. So my rho is 2. And because rho is greater than 1, we know that this is divergent. So the series diverges. And we can say our original series up here is divergent by the root test.